Rishabh AGARWAL, qui est chercheur principal chez Google DeepMind à Montréal et professeur adjoint à McGill. Après une année avec Jeff Hinton à Google Brain, il a fait son doctorat à Mila sous la direction d'Aaron Bourvil et Marc Belmer. Ses recherches portent sur l'apprentissage par renforcement profond avec des applications aux problèmes réels. And I'll say that again in English. Rishabh Agarwal is senior research scientist in the Google DeepMind team in Montreal and adjunct professor at McGill. After a year with Jeff Hinton at Google Brain in Toronto, Rishabh did his doctorate at Mila under the guidance of Aaron Bourvil and Marc Bellemare. His research revolves around deep reinforcement learning models, often with the goal of making reinforcement learning methods available suitable for real-world problems. He also received an outstanding paper award at NeurIPS. What year was that?
That was like, I think 3 years ago.
Okay, very good. Congratulations. We might have some of the co-founders of NeurIPS in the virtual. Steve Vincent, he usually comes to this. The talk is many-shot in-context learning. And everyone who knows it, who's received the notices and who's here has read the abstract, so I won't reread it. I'll just say that Rishabh agrees to answer questions during the presentation as well as during the Q&A. Et si vous avez des questions à poser en français, vous voulez la traduction, vous n'avez qu'à lever la main et je vais lire la question. Okay, with that, I welcome Rishabh and I turn it over to you.
All right. Should I start or should I wait a couple minutes?
We could wait a little bit more if you want, but
okay, let's start. I think it's fine.
Let's start.
I have to leave. Yeah, hi everyone. My name is Rishabh, as was introduced, and today I'm going to talk about our work on many-shot in-context learning. So just before I go into the details, do people know what in-context learning is? And
assume not. Define everything.
Okay.
The people here present in the room are actually in computer science, but it's always a good idea.
Yeah. So I guess this in-context learning is the idea that you can show your language model a few examples and then ask it to solve another, basically. So you have examples are input-output pairs. And let's say you give it like 4 examples or something like that. And then you give it another input question. And then you expect the language model to get the right output for that input question. So basically, let's say if it's a translation task, you show it English, French, English, French, English, French. And then you give it a new English sentence and hope that the language model can generate the right French translation for that. So hopefully that makes it clear what I mean by in-context learning, which is the language model is learning from examples in context. All right. So this work is also accepted at NeurIPS this year as a spotlight presentation and was done with a large set of people, including, I guess, from Montreal, it's just me and Hugo Larochelle, who some of you might know. All right, let's move on. So I just mentioned about this thing about in-context learning, right? And I said like, oh, we typically use a few examples of, let's say, English-French pairs, and then we ask the model to like basically solve a new input pair or new input example, like given an English sentence, give me the French translation for that. And typically, I think this has been done in the few shot.
Rishabh, your sound is off. Can you hear me?
Oh, my sound is off. You can't hear me?
Something's wrong with the sound.
You still can't hear me?
On vous entend bien? Yes, we hear you.
Oh, so the Zoom folks hear me, but not
Ici, donc qu'est-ce que je fais? Redémarrer. Mais quel ordi? Ah, Mylène, tu es là?
Recording in progress.
Okay, mais on n'a pas de... Say something.
Yeah, Can you hear me now? Works? Okay.
We hear you over Zoom.
Yeah. I think it was the UCAM folks who were relaying it, they couldn't hear. Okay, so just to, maybe I'll have to repeat myself a little bit, but on this slide, let's talk about what is in-context learning. So in-context learning is this idea that the language model can learn from examples in context. So assume, let's say you're doing a task of translation from English to French. You can show the language model a few examples of going from an English sentence to a French sentence. You do it a few times, and then you give it a new example. And that is what we call in-context learning, which has typically been used in the few shot regime. By a shot, so shot here refers to an example pair, which is English to French translation, could be the shot or something else. This is just the terminology we used. So now in this work, I think we are going to go from few shot to many shot in context learning. And why is that? So one thing which has happened over the last few years is the context length. And by context length, mean how many tokens or basically how much text can you send these language models has increased substantially. So in GPT-3, if you remember, which was released a few years ago, the context length was around 8K tokens. Well, now, if you look at something like Gemini 1.5 Pro, that is 2 million tokens. And by tokens, I mean these are the representations we send these language models. So we basically, rather than sending raw text, we tokenize this. But you can just think in your head, you can just generally think of it as text. And what has happened is we have gone from something like 8,000 to 2 million. So that is a large increase in the context length we can actually use for these sort of in-context examples. So we thought, well, what if we just send many short examples? So rather than sending, let's say, a few examples of English-French, what if we send thousands of examples of English-French translation? And does that help? So far, so good. Any questions? I am going to assume it's good. All right. So now I guess one question you can ask is, how many shots is many shot really? Because it's a bit vague. Like, what do you mean by many shots? So here I'm just putting this as a picture of what is the number of shots we tried. So typically, like you can see context length on the y-axis, which is, so for few shot examples, it's like up to like 3,000 tokens, let's say generally. As we go from few shot to many shot, you can see we tried from like something like 125 shots on a bunch of tasks to up to actually even like 8,000 shots on the sequential parity tasks. So we really try to send a lot of examples. And you can also see the context length. So we basically went up to a context length of 500,000. Yeah, is there a question or something? Okay, no, that's just an invite. Cool. So basically, by many shot here, I mean we just tried like an order of magnitude more examples than what is typically done when we are dealing with few shot learning. And I think maybe it's worth mentioning that this was the initial excitement around these language models, that these models can learn from examples in context. They don't have to be fine-tuned for each new task. They have this capability of doing meta learning. Just by showing them what we want them to do, they can do it. Hopefully so far so good. And I guess just to show you what happened when we did this, we actually saw a large performance improvement across the board on different tasks when we went from this few shot in context learning regime to many shot in context learning regime. And I'll show like a few specific examples, but you can see like we saw improvements of even up to like something like 18% or more on some of the tasks. So basically this in many shot in context learning has a lot of potential, and all we had to do was just send more examples. So let's say next time you're trying to use your language model to do something, rather than asking it to do that, what if we show some examples? And then maybe you can even do better. What if you just send like hundreds of examples or all the examples you have and see what the language model comes back with? Okay, so hopefully so far, like your attention is here that maybe this many shot thing can actually do things much better than few shot. So let me just give you some very specific examples to tell you what we managed to achieve with this sort of thing. So the first example I'm going to give you is this task of low resource machine translation. And I think we picked this task because language models are currently not so good at this task, because this requires a lot of knowledge about these low resource languages. Here we use two languages, Kurdish and Bemba, which is, and by low resource, I mean there's not as many like documents on the internet about these languages, or generally we don't have like a lot of pair data between English and Bemba or English and Kurdish available to us. So basically what we see is that as we add more and more shots, and by shots again, just think of them as examples or translation pairs from English. Let's say if you look at English to Bemba, so shots mean more translation pairs from English to Bemba. You can see performance goes from something like 30% to up to like 45% or above, and it actually even surpasses the state-of-the-art performance we have. So in some cases, we even outperform the Google Translate performance or the state-of-the-art performance with this specialized system called NLLB, just by adding more examples in the context of the language model. So hopefully this at least shows what could be achieved with many-shot in context learning. Okay, let me continue forward. Another thing we tried is this task of planning. So here it's the task of logistics planning. I think here it was something like you have to deliver parcels from one city to another. I think it's a very common task used in computer science often. But basically you have a couple of trucks. You have within the cities, you have some ways of transportation. Across cities, you can use something like airplanes and whatnot to transport packages. And then the task is to come up with a solution so that you can do like basically optimal planning for this kind of package delivery task. And again, what we saw was basically as we add more and more examples, performance improve. Here I'm showing two versions of the same model. One earlier version and a second one, which is the better improved version. So the green one is the version which was released early on. And then the blue version was the one which the model API was updated, and it's a much better version, as you can see from the zero shot perform or like few shot performance at the initial point. When I only showed one example of what the task is, it gets around up to 40%. But as we keep adding more and more examples, you see a monotonic improvement on the blue curve. Basically, the model gets better and better at this task of doing planning. Hopefully, so far so good again. Let me move on to one more example. So here, I think this was a little bit of an interesting task. Maybe I should have shown the prompts. But this task is the task of verifying a piece of code, which is I have like a simple code problem. I'll think of it as a grade school math problem. And I'm writing code in Python to solve this problem. And now my task is to verify whether this solution is correct or not. So what we are learning is a verifier of code, which is verifying correctness. It's not doing like, I guess, whether this code executes or not. What we are trying to verify is whether this piece of code correctly answers the problem we wanted to solve. And yeah, so basically now you can apply. So this is a classification task, and you can still use many-shot in context learning by showing it more and more examples of what is good piece of code which correctly answers the problem and what is a wrong piece of code which doesn't do it. And again, as you see, as we increase the number of examples from 1 to 128, performance generally goes up. Here, the way we are measuring performance is basically we use this verifier to do best of 4. What do I mean by that is basically we show it 4 solutions at test time and ask it to pick one. And basically, if it picks the right one, then accuracy goes up. Otherwise, it can also pick the wrong one. So basically, it gets a 0 if it does that. And if it actually was the perfect verifier, it would have gone to 90%. But because it's still like not the perfect verifier, it learns it's still wrong on a lot of problems. It only gets up to 82. But still, that's a big increase of performance from 76% to 82, which is we basically bridged the gap or made the gap half after adding these in context examples. And on the right, what you see is what is the model learning. So here it's a very simple task, right? Either a piece of code is correct or incorrect. So we looked at whether the model was actually getting the right answer for the correct solutions and incorrect solutions itself. Like what is the confidence of the model when it sees the correct solutions and when it sees the incorrect solutions. And I think we saw one peculiar finding here. And the finding was that basically the model is very confident when it sees an incorrect solution. And that's why it assigns a low probability of being correct, like P of yes given correct, which is the solution correct, given it was actually incorrect, is very low. It's like from 0.3 to like 0.1, especially it decreases even more when we add more shots. But if you look at the probability of saying that a correct solution is correct, that's also low, actually. So the model is very confident about incorrect solutions, but it's not really that sure about correct solutions. Although the nice thing is it does say that, oh, a correct solution, it feels that a correct solution is more correct than an incorrect one based on its probabilities assignment it is doing. But that's interesting. It's like it's a one-sided basically classifier almost, that it's very good at one of the classes, while for other classes it's not that confident or sure. Does that make sense? Yeah, I guess maybe at the end I'll show some examples if people are a bit confused about what's going on there. But again, think of it as I said, this problem was verifying code. So the inputs are, I give you a problem, I give you a piece of Python code, and then I tell you whether this is correct, so yes or no, and I just show more and more examples like these. So that is what in-context examples here would look like. All right, I think I can continue. So assuming everyone's following, let me just go to the next part. So I guess there's a lot more examples in the paper. So I showed some of them like on planning tasks, but there's summarization, there's other reasoning stuff and whatnot. So let me go to like more interesting bits about the paper. So any questions so far about the part we discussed? That so far the claim has been, as I add more examples, performance generally seems to go up, although it can plateau or degrade with too many examples also. Assuming everything's good, let's continue. So I guess now we investigated this question of what if we can do many short learning without human written rationales or examples. So far what we were using is we were using like the ground truth outputs, or basically given input, what is the ground truth human written output for that input. And we're assuming that we have access to these data, that we know what the right answer is, and basically what the right rationale is for these answers. But what if, let's say, we don't have access to the human written rationales or solutions? So let's say if you're doing math problem solving, let's say all you have is just the final answer and not the intermediate solution. Can you still do something with it? And I think this is the part which we investigate in this half of the talk. And so there are two things we tried. So obviously, and I think the motivation behind this is that these human written rationales or demonstrations can be expensive to collect. So can we just do without them? And the first idea we had was, well, what if we generate these rationales? And by rationale, I mean like basically a step-by-step explanation from the model about what it wants to do. So let's say if I give it a math problem and you ask the model to think step by step, come up with a solution of the math problem. That is what let's say this is called rationale or solution rationale. And then what you can do is you can filter all these rationales which are producing the right answer. So let's say you ask the model to basically solve the problem 5 times, and it generates a different solution each of the time. What you can do is you can basically take these solutions, pick the ones which got the right answer, and just use those. And then you can compile these filtered rationale as in-context examples. So let's say, yeah, so you can see the process in this slide that I generate multiple rationales for each problem. You filter these rationales using whether they got the right answer or not. And that's a very weak kind of check that the model's just basically outputting something that ends up getting the right answer. It may not be correct, but we're saying that maybe there's still some learning signal in these. And what we do is now we just pair up these problem rational pairs as many short examples. So you show them a long list of these in-context examples generated this way. And I guess we call it reinforced because there's like the people in the crowd who know about machine learning a lot. It's actually related to this thing called expectation maximization based RL, which is if you were to train these models on these examples, it would correspond to a version of RL, which is related to expectation maximization. But here we are not doing any sort of training. All we are doing is basically showing the model the example in context. Okay, so that was one of the things we tried. Another thing we tried, and I think this might sound a bit more crazy, is basically what if we just get rid of the solutions altogether? Like what if we just show the model the basically what it has to do, but also a long list of problems. So rather than, let's say, showing it problem solution pairs, what if we just show problem, and then at the end we say we have an instruction saying, oh, you now need to generate problems and solutions, or we show it like a couple of problem solution pairs. So basically we are teaching the model what kind of problems it might be asked, but we're not showing it actually what are the solutions to these problems. And this is what we call unsupervised ICL. So I guess the motivation behind this was saying, well, if the model contains all the knowledge already there is to solve this task, maybe we don't have to show it actually what it has to do. Maybe it can figure that out. Maybe showing only the fact that, oh, this has to do this sort of thing might itself be very useful. Does that make sense? Or do people have doubts about this one? So this is very different from what we have been doing so far. So far, we have always been doing input, output, or problem solution. But here we're just saying, okay, what if we just show it a lot of problems and then ask our problem with an instruction saying, oh, you need to solve these problems, but these are the kind of problems you will need to solve.
Rishabh, let's check whether you can hear me. I'm going to turn off this one.
Yeah, I could hear you. Okay, so far so good. Let me show you what the results look like for this, assuming people understood. So this is what we got. And I think the results are a bit interesting if you look at it, or at least mysterious. So one thing we found was, first of all, using model-generated rationales were actually better than ground truth human-written rationales. So there are like 4 colors here. The light green color is ground truth. The teal color is unsupervised ICL, and the blue color is reinforced ICL. And what we are solving this on, I guess, these math problems, these are like high school competition level math problems, as well as grade school math reasoning problems on the right-hand side. So let's focus on the left-hand side plot. And what we found was actually using model-generated rationales was actually better than using ground truth rationales, and also just not using any solutions at all. Like just giving the model the problem that it needs a lot of problems to show, and then asking it the problem we wanted to solve actually could be better than using the ground truth also. And it could be actually competitive with using the model-generated rationale, so sometimes even better depending on the number of shots. But we see like an improvement in performance from around 50 to 58% as we go from, I guess, 4 shots to about, I guess this is 25 shots. And after that, performance seems to plateau generally. But this was interesting that you can see that the ground truth color, the ICL plot with the greenish hue, that was always lagging behind these 2 approaches. And the other thing we tried is whether these sort of prompts generalize to a totally different task. So here, though, even though we were using these high school competition math problems, we wanted to check whether giving those as examples to the benefit solving grade school math problems. And again, we found that actually there was a big benefit of doing so. And performance was generally more monotonic here, that we can increase the number of shots up to 250 rather than 25. That you can see that the blue curve or the blue bars are generally going up slightly as we keep adding more and more examples. And they, again, outperform using either the human-written solutions or just not passing in any solutions at all. This was a bit dense, I think, hopefully, but it makes some sense. That what I'm saying is, rather than using human-written rationales, what you can do is you can use model-generated rationales and filter them with some sort of check with how good these rationales are. Or you can get rid of these rationales altogether. And I think math reasoning and other stuff, at least these data sets or benchmarks, so my intuition is that there's a lot of training data that focuses on math reasoning problems or math problems specifically. So the underlying model has a lot of knowledge already about solving these kind of problems. And that's why we are able to get rid of the solutions altogether. Let me show you another examples. This is called,
can I ask a question?
Yeah.
Can you go back there? Yeah. So why do you think giving in the left graph, the ground truth solutions, giving it the ground truth solutions as you add more and more gets worse?
Yes.
Why do you think that is?
Yeah, that's actually a thing we found for a lot of models. And the reason I think is simply, there are a bunch of reasons. One is these models are actually never trained generally to actually see a lot of examples. So we never fine tune or train these models to show where we actually show them a lot of examples and ask them to do like solve this given input or do the right thing. We always train them to only with like a small number of examples. So one thing, it could be as simple as just distribution shift. It's just like magical that, oh, these models, even though they are never trained to deal with a lot of examples, they're still able to do so at test time. That's one. The other is about context length limitations. So sending in about, like, I think if you look at, so first of all, with the ground truth, there is also a thing that the kind of distribution of solutions of human written things might be very different from what the model likes to generate, which is let's say, or maybe to put it another way, let's say the model has a certain set of skills, and let's say the human written solutions use some other skills which the model doesn't have. So let's say the human written solutions use something like how to solve an integral, which the model doesn't know clearly how to do. Then maybe that example, rather than helping, it might hurt. Because you see, like, we don't see the same kind of degradation with model generated solutions. So there are like two things, maybe mainly. One is ability to deal with really long context lengths. So even though we have really long context, the models have never maybe trained with such long context lengths generally, especially this kind of context where we show them a lot of examples, at least for this work. So that is possible that once we go beyond a certain length, things just start to become worse. And we saw it on other tasks too. The other is, I guess, the distribution of input-output pairs. And here I'm saying that ground truth inputs, again, input-outputs, may not be as in distribution compared to, let's say, the other kind of input-output pairs. Does that make sense? Or does that help?
Yeah, I guess I like the answer that it's not the kind of solution the model itself would generate.
Yeah, I think the other thing is this degradation is very, very task dependent. So on some tasks, we saw it clearly. On others, we could keep going up even to up to 8,000 shots and things didn't change. So I think it's still, this is something we are still trying to figure out what's going on, but maybe helping or fine tuning the model further with these kind of examples might help. And I'll come to that also at some point. All right. Any other questions? Yeah, thanks for the question. Okay, so let me show another example of the same thing. So this was like math reasoning kind of tasks, but there's another set of tasks, we call it, and these are like algorithmic and symbolic reasoning tasks. And these are like very simple tasks, like, I guess, from things like multi-step arithmetic, which is you have to just add like a few numbers, or not add, you have to just do some simple arithmetic operations between 3-4 numbers, or to things like basically sorting. So word sorting is another task, or this DIC languages is a bracket matching task that I give you a bunch of brackets, and then you have to finish off so that the brackets are closed properly. So you have to add more brackets at the end. So it's like sort of the stack-like solution we typically do in computer science. Or things like object counting, which is I give you a list of objects and I say, oh, how many objects there are. So it's very, very simple tasks, but our current language models do struggle with these kind of tasks, depending on what the task is. So again, we saw that actually, so we have like typically here we use a 3-shot chain of thought prompt, which is like a problem, solution, rationale, and then the final answer. And what we did was we used this prompt to generate rationales for a lot of these other problems to put them in context. So we use up to 100 problems. We generated these, I guess, model-generated rationales, or I guess in unsupervised ICL, we just showed them these 100 problems that, oh, these are the kind of problems that you would need to solve. So, and we saw that both of them actually generally improves with, again, reinforced ICL working much better. So on some tasks, you can see that there's a big gap between this reinforced ICL and unsupervised ICL. Both of them do seem to actually do better than the ground truth 3-shot human written prompt. So one trend, there are a couple of trends you'll see. There's some noise in these plots, but generally performance goes up as we increase the number of shots. So you can look at most of these curves are going up, and the slope of the unsupervised ICL curves are slower, which means basically they're not going up as fast as reinforced ICL and doing a bit worse. But they're still able to outperform the human written prompts in some cases. So if you look at reasoning about colored objects or logical deduction, they are actually able to do a bit better than the human written prompt itself, or the human written prompt with 3 problems and 3 solutions. All right. So hopefully this was good enough about these 2 methods. So these are basically 2 new approaches to like use if you don't have access to the ground truth human written rationales, but you have a way to check the model generated rationales, or maybe you can just get rid of the rationales altogether and see if that works, because maybe the model already has some knowledge, and depending on the task. On math reasoning, I think we saw that unsupervised ICL was working quite a bit well, even better than the ground truth rationales, while on this algorithmic and symbolic reasoning task, that is not really the case generally. Okay, let's move on. And now I think I'll go to more analyses part of this work, which is what is going on, and maybe it'll raise a lot more questions about how does this in-context learning ability work generally and what it can achieve. So here it'll be less focused on these tasks or methods, but more about, okay, what is really going on? So I guess this is the this is part. Any questions before I go there? All right, let's continue. So I guess one really interesting finding we had, and I think I'll spend a bit more time, is that we are able to see that we can actually overcome pre-training biases using this many shot in context learning. And what do I mean by that? So here's it's a very simple sentiment analysis task where we have to classify some sentences as positive, negative, or neutral. So let's say I'm very happy. That's a positive sentence. Or I'm feeling not so great, or I'm feeling sad. That seems like negative sentiment. The other is I'm overworked. That's neutral. So this is just like analyzing sentiments of different things. So what we did was we said, well, what if we actually change the labels of these tasks? We keep the input sentences or the sentences to classify the same, but we can do actually two kind of like flipping or changing of labels. Sorry, someone saying something. Is there a question? No, okay. I just heard a sound. So, okay, so there are two kind of changes we did. One was flipping the label. So one was abstract. So rather than calling them net, neutral, negative, positive, what if we just call the labels ABC? So we remove the sort of information they have in the fact that I'm calling I am feeling sad negative. We just call it now ABC. So there's not much information left anymore. And the harder task of flipping the labels altogether. So we are remapping these labels. So what we did was we called any negative sentiment sentence as neutral, any neutral sentence is positive, and any positive sentence is negative, which is I am very happy will become a negative sentiment, or at least the model will be given the task to classify it as such. So this is not possible without showing it in context examples, because this is just like a very bizarre mapping that I ask the model to predict negative whenever I give it some really positive sentence like I'm happy, while if I say something like, oh, I'm not feeling good or I'm feeling very sad, that has to be like, let's say, that's a negative sentiment sentence, but we ask the model to predict neutral now in this case. So hopefully people understand what the setting is. So let me just like show you if you just have the default labels, which is the model is doing sentiment analysis task, the performance of the model is very high. It already starts around 85% or I think 90%. And then as we increase more shots, the performance improves a little bit because there's not as much room to improve, and then saturates. But if you go to like, let's say now if you go to this abstract label task, which is the teal line here, you see, first of all, the performance drops rapidly because the model doesn't have any notion of what does A, B, or C mean. So it has to look at the examples. So here, the leftmost point of the plot is 4 examples, and then we increase the number of shots. And you can see that eventually with enough examples, the model is able to catch up to the performance it had with the default labels of negative, neutral, positive. Which is like with enough information, it can learn what the right mapping is. And now I think, let me talk about the dashed yellow line. That is the flipped labels, where we change things like negative sentences are called neutral, while positive sentiment sentences are called negative. And so this is like a much harder task. And you can see actually there is like also some sort of fight going on within the model that as we increase the number of shots initially, performance goes up. And I think we had an analysis in the paper showing that what is going on is that the model is figuring out its confidence, and it's really confident initially, and then as we show it more examples, it's getting less confident, and because of that, it's also dropping in accuracy. But then beyond that point of 2 raised to power 3 or 8 shots, performance generally goes up, and again it catches up nearly with the performance it had on the default labels. And this is actually a task which is not possible if the model was not looking at these in context examples, because it is basically at the end of the day saying, oh, I am very happy is a negative sentence in this task. But with enough labels, we're able to see that, oh, we can actually override these biases, because this kind of bias, why do we call this like I am happy as a positive sentiment sentence? This comes from pre-training. And we are showing that actually we are able to like basically remove this bias or overcome this bias substantially just by using in context examples. So this is like a nice finding showing that, hey, like we can actually teach the model something they might have learned already, but we can actually like fix that. If that whatever they have learned is not good or something along those lines, maybe we just need to show them a lot of examples and we can fix that. And also vice versa is also applicable. Like some bad actor can obviously show the model a lot of bad examples, and I guess make the model do things which, let's say, it is fine-tuned or trained not to do. So this is called many-shot jailbreaking, which I think it's a very fun paper also, where they do things like they show the model a lot of examples of doing things like make a bomb, do this thing, write hate speech or whatever, and then the model actually starts doing that, even though it has been trained not to do that. So you can override these biases from pre-training either way. Okay. Hopefully this was like, maybe people understood this. If people didn't understand, feel free to like, yeah, this is maybe the right time to ask a question. Okay, let's move on. So the second task we tried was, and this is now much more bizarre than all the tasks we tried. So far, we're dealing with like these tasks about, like, I guess, texts, or we will give it natural language and ask it to do something in natural language. Here, what we're doing is we're just giving it like a bunch of integers. Or so here, what I'm doing is like, basically I have random sequences of integers. Each sequence can have like, I think it's let me see what it is. Yeah, so it's like number of, so n here on the top on the plots. So we tried like 16-dimensional to 64-dimensional sequences, and each number in the sequence could be any integer from 1 to 1000. So basically it's a large space of integer vectors, and we're basically giving these vectors a sequence of numbers and then labeling it as a class. So either the class is 0 or 1. And we are showing these examples to the model as like charts. So basically, we are showing it like a bunch of these random sequences of, let's say, a given length with the corresponding label we already decided. And now we are just showing the model the more and more of these examples. So basically, a sequence of numbers, their class, and then how many examples we show per class. And the finding we had was actually that the model's many shot performance, as you can see, it fluctuates, but it actually tracks very well k nearest neighbors. So this is like non-trivial, that the model is able to implement, and this is not even text. This is just like random sequences of integers. So there's no way the model actually had any kind of data like this. Well, it's hard to say, but generally this is not the kind of data which would be there on the internet, because this is like really random sequences. And what we find that the model was able to implement k nearest neighbors in its, at least in the output, that's what it looks like, that it's very close to that. And you can see some of the degradations also happen with k nearest neighbors, that even the performance of k nearest neighbors is not monotonic. It does go down as we add more examples sometimes due to just the noise, I guess, or it's not as easy to solve these high dimensional classification problems. And obviously, it's doing much better than random performance of 50%. And again, as you increase the dimensionality of your input sequences, things get harder. So that's why you see the plots are going down. So the gains are also going down. But generally, it's tracking the k nearest neighbors algorithms. So that's very cool that it's able to implement really like classical machine learning algorithm just using in context examples. So there's no training involved here. Was this example clear?
It's a binary classification task. Did you generate like class 1 from a prototype and class 2 from a prototype with Gaussian noise or something added?
Yeah, that's a good question. So what I did was this. I took like a random vector in high dimension, and then basically whatever other so this is the vector I use, and then whatever other vectors I generate, I take a dot product with this vector, and if the dot product is below a certain threshold, I call this positive, otherwise negative.
Okay.
So this was following some other work, but this is like much more random than having Gaussian noise, I guess, because I am really picking an arbitrary direction. And I repeated this experiment like with, I think, over 10 times or something. That's why you see large error bars. But basically, pick a random vector. This is your, I guess, the decision boundary almost. And if things are close to this decision boundary, then we call them positive. If they're really far from it, you can call them negative.
Okay. So it was one prototype essentially.
Yeah, one prototype, and then repeat this experiment again with like, I think 10 more times, just with random prototypes.
Did you see any difference depending on what the threshold was?
That's a good question. I think so. Sometimes I saw that when the threshold was too small, it was a really hard classification problem, and that's where the drop was much more. While if the threshold, because that threshold was also picked randomly, but if the threshold was large enough, then the model had an easier time fixing it. And I think this was also applicable to k nearest neighbors. That if the threshold is really small, the model is not sure that, hey, like this is positive or negative, because it's not able to like check for the points which are really close to that threshold. So it's always the points which are close to the threshold that the model had issues classifying. So it's almost like trying to learn a classifier akin to k-nearest neighbors, but still struggling to do so that well. But yeah, no, this is a very easy experiment. This doesn't require any sort of data, and I think you can play around with this with any existing API models you have and see what happens. And I think we picked it from some other work which we're trying to do this analysis, but only up to like a small number of shots. Here we expanded that to 2 raised to power 11 shots. So that's around 2048 shots. I think this is 500,000 tokens, I think, just to do random. So if you look in the how this is represented, just to do classification. So that's pretty long context length here. Okay, I guess I'm assuming no other questions. So let's move on to another. So here, I think it's a more interesting setup where this is a bit different. So here, what we're trying to do is we're trying to predict sequential parity of a sequence. And what do I mean by that is, let's say you give it a sequence, a binary sequence of ones and zeros. And then we ask the label the model has to output as this odd, even thing. And what it is the parity of the sub. So for each position I, it's the parity of the subsequence up till that. So 1 is odd, 1, 0 is odd again. If you look at the parity, 1, 0, 1 is even, because there are 2 ones now. 1, 0, 1, 1 is odd, and that's what the label corresponds to. Right, and people have shown that these kind of tasks are really, really hard for these language models. And what we again found was, and here I think maybe it's more fun, that first of all, we saw that the performance was monotonic up to 2 raised to power 13 shots, which is, we send around 8,192 shots here, and performance generally kept going up. And there were like, basically we fine-tuned a small transformer model to solve the same task. And what we found was they actually needed about like, I think 20 times more example to reach the same performance that we got just by in-context learning if we were to use like a small transformer from scratch. So basically, if you show it 20 times more examples of this task, it can actually get the same 40% accuracy. And if you keep training it, I think it eventually solve it. But it's an interesting like finding showing that, hey, like you're actually 20 times more sample efficient because you're only learning from things in context itself. So you're able to actually learn much faster. And here, the random chance accuracy is 0. The other thing is this is very different from the k-nearest task. So here, the model has to implement some other algorithm because if it implemented k-nearest neighbor, it'll always be off by 1 digit. Because the nearest neighbor for each given sequence would be something which has 1 digit, which is different, which means the parity label would be off by 1 digit. And here we are measuring the exact accuracy or exact match accuracy, which is whether it got the parity of each of the bits right or not. Or each of the subsequences, right? So even if it makes one mistake, we just classify that as a 0, or we just do not score it positively for that. So this was interesting. This is very different from, like, it is not doing k-nearest neighbors here, because k-nearest neighbors will get an accuracy of 0% on this task, because your nearest neighbors are always off, or all of your nearest neighbors are always off by 1 digit, or at least they have 1 digit which is different, which means that the parity output would also be different. So here, I guess this is kind of showing that at least there is some sort of learning going on here, which is just not k-nearest neighbors or something else at least.
So can I ask a quick question? So I guess because random isn't 50%, you're deciding on the label if all the 20 are correct?
Yeah.
Okay, that makes sense.
Yeah, and also you have to look at the previous subsequence. So it's not looking at just at that digit, but the sequence so far. So it's kind of easy. The labels are not that hard, because all you do is you look at the parity of 1 bit, then you look at the next bit, you keep computing the parity based on the previous one. So if you have odd, even, and then you see a 1, then the parity would become odd. If you see a 0, then the parity would remain even. Okay. So this is at least saying that, okay, this is not all, because there's like a lot of debate in the community and literature around what is in context learning? Is it just memorization? Is it just like, I guess, some sort of Bayesian retrieval and whatnot? And I think this kind of result shows that, okay, this is definitely not memorization, and there might be some sort of learning going on here. While this sort of result, which I just presented, was saying that, hey, maybe there is some sort of retrieval-like methods here, or like k-nearest methods implemented. And then I also discussed this unsupervised thing, which basically hints towards retrieval. So it's a mix. Depending on the task, I think in-context learning might have multiple modes. And one is like some sort of task retrieval mode, and another is a task learning mode. And there are theoretical works also arguing for that it's possible with enough examples, the model switch from some sort of retrieval mode to a learning mode. And it is very dependent on the task, whether how much you know about the task and a bunch of other factors, which I think people haven't still figured out. Okay, let me move on to another analysis experiment. So one thing we did was how far can we push this compared to, let's say, fine tuning, which is if I have a small number of examples, one option for you is typically, or what we do in machine learning is we train the models on these input output. And the other option here is what if we just send these as like basically in context examples. So fine tuning has a cost that you have to update the weights of the model, and it is computationally expensive the bigger the model is. While in context learning, all you are doing is that inference time, you're feeding in a lot of examples. So there's no training cost at all, but there is an inference cost, which is the model has to parse all these examples. But there are a lot of optimizations these days, like KV caching and other things, that we try to make this really fast because this is a common use case. So the interesting thing we saw, at least for this task of low resource machine translation, that many shot performance was actually very close to the performance of supervised fine tuning, which is, I think, the first time people showed that, oh, in context learning could actually match fine tuning performance. But basically, this is a very nice finding, and we don't know like how far we can generalize this or how well this generalizes to other tasks. But it's saying that rather than actually changing the weights of your model and making it specialized for this task, all you have to do is you have to send a lot of examples to the model at inference time, and that can actually give you comparable performance to fine tuning. So this makes prototyping very easier, which is whenever you have a new task and new things you want to do with this model, what if you just showed it a lot of examples, and basically it can actually get similar performance to fine tuning. If this was like, I think this is what, if let's say we were to get too close to this thing called AGI or general artificial intelligence, I think this is something like we need, that rather than actually training the model for each new task we see, what if it can just learn from in context examples? Basically, let's say is this model, if this is deployed in some sort of real world application, what if it just sees the impact of its actions, and then based on that it can just learn what to do? That is, I think, at least would be a starting point for getting much more capable models. I don't know where we are there, but this seems promising if this generally holds, or if we can actually make the future versions of these models so that they are able to just learn from in context examples, because then you don't have to keep adding new data for each task that you have to solve. The model can just learn from the test time examples itself. Okay, let me show maybe, this, I guess before going to this, let me show this result that we found that this ability was not consistent across models. Like we saw some models were much more stronger than others in able to do this in context learning thing. And I guess one interesting thing was, so I'm showing two Gemini models from Google, and I guess GPT-4 Turbo from OpenAI and Claude 3 Opus from Anthropic. But basically, Gemini 1.5 Flash is a smaller model than 1.5 Pro, and it generally performs much worse. But that smaller model also had very strong in-context learning abilities. So you can see the green line starts very low in terms of few-shot performance, at least on the English to Bemba tasks. But with enough shots, it can actually surpass or match the performance of both GPT-4 and Claude 3 Opus, which is a nice result. It's kind of showing that, oh, even though some models may not have all the information they need to solve the task, just by showing it the one example or two examples, if we actually basically send enough in-context examples, they can actually outperform these stronger models. That's nice. That gives you a way to actually use your small models and make them better just with in-context examples. Okay. The other, I guess, maybe this is clear. Let me just go to another thing. One more thing we asked the question was, I guess, is it likely because we are increasing the context length quite a lot, or are we sending in a lot more information? And that's where the performance gains are coming from. So what we did in this experiment was we said, what if we just send the same 25 examples, but repeat them? So basically, we repeat them twice, we repeat them 5 times or 10 times. So that's what the red bars are. And the green bars are just adding new examples altogether. So both of them will use the exact same context length or exact same amount of tokens that we are sending to the language model. But one of them, the green one, is sending more information because there's new examples in context examples, while the red one is just repeating the same information. It's controlling for the length of the information we send. So in one case, we are sending like a lot of information, when other case, we are matching the same amount of length or tokens we are sending, but we are repeating the information. And we saw that the most of the gains, at least on this translation task, were coming from new information rather than just having longer lengths. Okay, and I think maybe this might be the final slide of this talk, that we found that as we add more and more examples, the model's next token prediction ability becomes much better on the ground truth solutions, which is, if you look at the log likelihood of the ground truth solutions, or whether the model is able to predict next tokens on the test solutions, we saw that it generally becomes much better. But as we saw earlier, the in-context learning performance does degrade after a certain number of shots. So this does not explain. So next token prediction here does not explain why the performance was dropping. The other thing is, we also saw that negative log likelihood for human written rationales is lower, which means the next token prediction loss is lower when we are using the ground truth examples compared to the model generated examples or model generated solutions. But the accuracy trends were reversed, that model generated solutions were doing much better. So this is also another example or another indication showing that this is not a good proxy, that next token prediction loss on human written solutions may not be a good proxy to predict performance of these models, at least in case of many shot ICL. So this is like Lily saying that maybe we need to do some sort of other sort of indicator. Like, this is a very, very commonly used indicator, but at least in many shot ICL, it doesn't explain what's going on. And I think that is the summary. So, well, many shot models can improve performance up to thousands of shots. They can even outperform, or model generated or unsupervised prompts can even outperform human written prompts. And I think there's a lot of future questions which we didn't answer. So what are the mechanisms underlying many shot learning, and why do some tasks benefit a lot more than the others? And I guess also this question which was asked, why does performance really degrade after a lot of shots? And this I didn't cover, but we also find that there is a sensitivity to example ordering. Maybe let me just go there quickly to show this. So we found that on the x-axis, I'm showing like a bunch of different splits of the same data or same set of questions. And on the y-axis, I'm showing like what happens if I change the order of the many shot examples. And each color represents a specific order. So we saw that actually some orders are really good for some.
Can you hear me? Rishabh, can you hear me?
Yeah, I can hear you.
There's something strange. There's a lag between when you change the slide and what we see. We're still seeing the summary. Now it came.
Oh, I see. Maybe it's just internet. Okay. Sorry.
Is this the slide you want to show? Many shot ICL?
This is the last slide. Yeah. Okay. So one, I think, weird thing that we didn't understand but did happen is that the performance was very sensitive to example ordering, and each color here represents an ordering. And on the x-axis, each basically line or whatever, on the x-axis we have a different split. So each line or vertical line corresponds to the same set of questions. So we saw that some orderings are really good for some set of splits. So think about, let's say, the gray points. You can see that it is really good for two of the line, which is, I think it's while the same gray point is actually pretty bad for some other splits. So, and there's a large performance variation, even up to like 10%, which is a lot of variations on this benchmark, because people care a lot about like even a couple % gains on this. So this is another, and all I'm doing is I'm changing the order of the shots. I'm not changing the examples. The only thing I'm changing is which example comes first before another. So that is showing that, okay, this is one of the like, you can always optimize the ordering, but this is also an issue that the many shot learning is not as robust. That ideally it should not be, I guess, dependent on the examples, but because we are dealing with a model that treats everything sequentially, there is the ordering of examples matter, because it changes how the sequence is presented to the transformer or the language model. Okay, I think with this, I'll just stop at this slide. This is the last, sorry, this as in the summary. Let me go back to the summary slide again, and let me just stop there.
You're not at the summary slide. You're at the finish slide.
I see the lag. Yeah, it's gonna, maybe it's
gonna
take.
It'll come eventually. I don't know why that lag happens. Okay, it's open now to questions for either here in the lecture theater or in the virtual incarnation. I have also a list of questions from here, but I want to encourage those people who submitted these questions ask them orally now rather than have me read out your questions. Are any of you prepared to do that? Questions were actually gathered before you gave your talk. It was based on the readings that you gave, and so it's not clear that the dissociation. All right, let me use the chairman's prerogative to ask one of my own. I am not, since I'm not a computer scientist, I'm perplexed by the amount of information that you can get with unsupervised learning. I find it very difficult to believe. What can you say to reassure me that this is not sort of an artifact of, you say it's not memorization, and I believe you, but some sort of an artifact of the immense scale of data involved?
For the unsupervised ICL, no. So for that, I think I would actually argue that these are the kind of cases where the model has all the information it needs to solve the problem, and all we are doing is we are bringing it to the surface better. So this is like the Bayesian view of in-context learning, that all it's doing is some sort of fancy retrieval. And if it's doing that, then any sort of additional information that can help it with that sort of retrieval should be useful. So unsupervised ICL is saying, okay, then why do we really need the solutions? Maybe we can just use the problems, and that's still helpful. Obviously, this is not applicable for tasks, and I think I showed an example of that too, where the model doesn't have all the information to solve the task beforehand. Like, it needs to see what do we want out of the model itself. So I think, but it is intriguing finding that I think we didn't anticipate this to work so well. But our understanding is for some of the tasks, as you were saying, there's so much amount of data there on the internet and in pre-training or training of these models that maybe all we are doing is just bringing these capabilities to surface, and then any sort of thing which is relevant to these capabilities should help. So I think I didn't show you results of a much harder task. We studied a task which requires PhD in physics, chemistry, or biology to solve problems. And those problems are like hard enough in the sense that if you have a PhD in physics, you cannot solve the chemistry problems or something like that. And even there, we saw the large gain from this unsupervised approach. I think this is called GPQA in the paper. But on other tasks, like simple tasks, like sorting a list of words, we didn't see much benefits of this approach. So you can see like the contrast.
Let me ask a question from Dimitri Molo. Does this change your assessment of the effect of training on LLMs? Are you just listening in the background, or are you in a position to say something?
Yeah, I think it does. So right now, one thing that has happened over the few years, and maybe it's an unfortunate development, but initially the excitement around these language models was because of in-context learning, or the ability to learn from examples in context. Now that has shifted to the paradigm of we want these models to be really good generally without these examples. So we just want them, because I think the use cases of these models are, let's say, making a really good chat assistant. And if that is the use case, you don't expect the user to give it a lot of examples. You just ask the user is expected to give like a simple instruction like, hey, I want you to do this. Can you do this for me? And what has happened is we have actually now moved towards optimizing these models to become better and better at these kind of use cases. And somewhere in that, we lost this really nice ability of doing in-context learning. And I think that is very underexplored these days. So we're making models really good at like doing things really well directly without any sort of examples, but we're not really thinking about, okay, can we actually teach the models to use information at given a test time or learn from these examples in context only. So I would think that might be the main differentiation, or at least this is how I would want training to be changed after this work. That maybe we should also think about this capability.
Let me see if I can coax a little bit of more out of the people who are present here. Si vous préférez, vous pouvez poser vos questions en français aussi, mais posez-les, vous êtes censés d'interagir. Sinon, je lirai quelques extraits, mais je suis un peu déçu que vous êtes là passivement. Hello, Iris Iris. You asked some questions. You don't want to repeat any of the ones? Some of them are relevant with the present.
Okay, let me pull them up. But I don't
Yeah,
remember my exact wording.
Pardon?
I don't remember my exact wording.
Okay, I'll remind you. What you asked was what factors could explain the better performance of many shots, and that was addressed, and more particularly of reinforced ICL. And then you said, what should be the optimal length of context necessary for many shot ICL to be effective? And in terms of computation costs, in which contexts in many shot ICL is it more efficient than fine-tuning smaller models? Did you pick that up indirectly, Rishabh?
Yeah. So there were a bunch of questions. I don't know which, some of them were answered, but I can answer some of them. So there was a question about, I guess, why reinforced ICL is better. And I think the answer to that would be something like, or at least the hypothesis we have is that when you're asking a model solve a problem, it's only using the skills or capabilities it has, and that are more meaningful to learn from than, let's say, if a human writes a solution, because maybe they're using skills or capabilities the model doesn't have. Now, for computational, I think that's a very good question, and I think that's a question a lot of practitioners would ask. So one nice thing about many shot is because it doesn't require training or fine tuning a model, it's very, very quick to prototype. Now, fine tuning, you can fine tune a small model at test time, and you can fine tune a small model and deploy that. And I think there, obviously, you have to set up the fine tuning pipeline and all that. But at the end of the day, it depends on your use case of what is the efficiency you're able to get out of these systems. Because right now, a lot of these LLM providers are doing a lot of optimization so that you can send a lot of context and still your inference costs be very cheap. So at the end of the day, I think it depends on the exact costs. But maybe the only thing I'll add is the many shot thing can be very, very quick to prototype. Like you can do it like in 5 minutes or 10 minutes. While for fine tuning, it involves a lot more work generally.
Okay.
Yeah.
Anything else, Iris, or are you answered?
No, that's an answer. Yeah, I was, but I feel like that was also answered before, but I was curious about the computing costs of many shots, and that answers it.
I think we'll add it in the plot, but basically, if you use up to, depending on, so there is this thing called caching and whatever, but generally up to something like 32,000 tokens. So up to, let's say, something like 100 examples, you basically pay no cost, like it's almost zero. But beyond that, with each time you double your context length, you pay a linear cost in your computation time, which is, if it was earlier taking 1 second, now it'll take 2 seconds and so on. So basically, if you send really, really long context lengths, then you can think of doubling the context length would pay, you end up paying like a linear cost because of all the optimizations we do.
So that brings like another question, but so what's the optimal context length?
Yeah, that's actually a much harder thing. We also don't know because we tried prompt lengths on a log scale or logarithmic scale and see which one worked the best. And it was very task dependent. For some tasks, it was like using 100 shots, while for other, it was using something like 8,000 shots. So you can see the variation itself altogether. But I think, so this is my general advice. I would say just send the prompts. If you're trying this kind of idea out, just send them on a logarithmic scale, something like 5, 10, 25, whatever you saw in the thing, and just quick pick the point which seems to perform the best. So this is more empirical right now. But if there was some way of figuring this out, that would be nice.
Okay. Hamid Shirazian, are you here?
Yes.
You want to ask your questions, or do you want me to do it?
I prefer you do it.
All right. A second. So based on the author's suggestion that human involvement in evaluating the outputs of unsupervised in-context learning, ICL, experts can review the model's reasoning and outputs to ensure they are rational and contextually appropriate, thereby validating the model's performance and identifying areas for improvement. This is based on the author's suggestion. Considering the dynamic, so that's preamble, right? Okay. Considering the dynamic nature of emotion and regarding task-specific metrics to evaluate model performance, how would you suggest the evaluation process to contribute to cognitive load reduction and cognitive function enhancement. First portion. Anything on that? Yeah.
So I didn't understand what do you mean by cognitive load and like, is it like the amount of effort an expert has to do to review these things? Is that what the question is, or is it something else?
Yes, the metrics, the experts doing the review of the metrics, so they can adjust the input for feed forward, like with the some amendment to improve the cognitive load and enhance the cognition and reduce the cognitive load.
Did you hear that?
Yeah, I'm still trying to figure out. Maybe I can explain, or at least my interpretation of the question, and I can answer that. So I guess my interpretation was that experts, let's say, have to review these sort of rationales or like solutions. Can we make it easier for them to do so without spending a lot of cognitive effort? And if that is the question, then the answer is, I think we can use the models themselves. And this is what it's commonly done, that we basically ask the models to help the experts by basically trying to point out some issues or going line by line or something like that, and giving some sort of explanation about what this thing is trying to do, which the expert can use as additional information.
That answer for you?
Some sort of the continue of the
Speak loud.
yeah, but it is like have more efficient way, and we do it in more efficient way that after a while the model would be like trained and do it by themselves.
Yeah, that is, I think, one of the things we want in the future. But until we have very reliable models that can check their own reasoning, that is, at least right now, our models are not so great at checking their own reasoning. And I think that is the ability we need for this sort of thing. So that's a good thing, that I think we are trying to work towards it, or generally the community is trying to work towards it, but we are not there yet.
Okay, how about Button Shama? We ask it yourself?
I have to drop out in a couple of minutes because I have another after this. Maybe last couple of questions.
Ok, d'accord. Oui, ou bien je peux lire ce que tu as. I'll just to shorten, because our speaker has to go, I'll translate it. What are the two settings explored in many shot in ICL to address the limitations of human-generated outputs, and what are their effectiveness in complex reasoning tasks?
I think we just discussed that. This is a...
Okay, so that's taken care of. There's so many problems. Okay, so yeah, okay. Listen, you have to go. I'm not going to keep you. Thank you very much for your talk.
Yeah.
It's awkward with the link. You did an experiment on two languages, and we have two languages in the air here, but you're probably used to that at Mila.
Yeah, I think that is true.
Okay. Well, anyway, thank you very much for coming. I'm glad that I got through to you, even though the email takes a little bit longer to get through. And this will the talk will be on the series of talks here at the...
I'll share the slides afterwards.
Thank you very much.